Hi guys, and welcome to the first video of 7 Steps to a 7 in Olympiad number theory. This course will cover the most fundamental ideas in Olympiad number theory. We'll start out simple with familiar concepts such as modular arithmetic, and build up to harder ideas like constructions and prime factorization. But before we get started, I want to give a quick warning, and say that this course is not intended to be comprehensive. And there's so much more to Olympiad number theory than what I'll be discussing in this course in these 7 videos, such as, for example, quadratic reciprocity and Vieta jumping. I'm only going to be focusing on the basics. The intent for this course is to fill in the gap between familiar concepts, such as that on the AMY, to harder and deeper ideas which are essential in Olympiad number theory. That way, if you see a number theory problem on a math Olympiad you may be taking, you won't be like, oh no, what do I do? You'll be able to have ideas on it. And yes, I'm assuming that you are reasonably comfortable with qualifying for your country's National Math Olympiad. And for those of you in the United States, this is equivalent to around a 6 on the AMY. If you don't have any of these, then that's completely fine. Don't get me wrong. But I want to make sure that you're not learning material that is too hard for you to begin with. That's because from personal experience, if you do, then you will come out of this course more confused than when you first started it. You should start learning the material whenever you are ready to learn it. Please do not get too ahead of yourself. Alright, I've said enough. Let's go ahead and get started with our course. So as I said earlier, we're going to be starting out this course by looking at some pretty familiar concepts that you should know already. And one of these concepts is modular arithmetic. As a review, modular arithmetic is just a study of integers such as 1, 2, 3, all the way onto infinity when divided by a number n. And it's about looking at the remainders. So for example, 4 is equivalent to 1 mod 3 because 4 has a remainder of 1 when divided by 3, and so does 1. And we also say that this is equivalent to negative 2 because if you think about it, adding 3 to negative 2 gives 1, and adding 3 to a number should not change its remainder when divided by 3. Alright, besides the point, what is so useful about modular arithmetic anyways? Well, for one, we want to know if it's consistent or not, and as it turns out, it really is. What do I mean by consistent? Well, suppose you have integers a, b, x, and y, and we have some number n, and we're going to be looking at mod n. Then if we know that a is equivalent to b mod n, and x is equivalent to y mod n, then this implies that a plus x is equivalent to b plus y mod n. In other words, these two have the same remainder when divided by n if these two have the same remainder and these two have the same remainder. It's also consistent in the following way. So if a is equivalent to b mod n, this happens if and only if a plus x is equivalent to b plus x mod n. And what do I mean by this double arrow here, if and only if? Well, if and only if just means one is true if the other is true. If this one is true here, then so is this one. If this one is here true, then so is this one. And a lot of these properties should feel really familiar to you because in a way this works just like how the integers work. If two integers are equal, then adding an integer to both sides doesn't change this. And same thing for this one here. All right. And now we have multiplication modulo n. So suppose that a is a, let me go ahead and change color. So a is equivalent to b mod n, and x is equivalent to y mod n. Then this implies that a times x is equivalent to b times y modulo n. And ax is just the product of a and x, and by is just the product of b and y. and they have the same remainder when divided by n. And can we say something similar to the second item about multiplication then? Well, almost. Suppose that A is equivalent to B mod n, and that means that AX is equivalent to BX mod n. But how come I never did this if and only if arrow here, just like how I did over here? How come I never put an if and only if over here? The reason why this happens is because multiplication can act really weirdly. So for example, suppose we're taking mod 4, so n is equal to 4. Then we know that 0 is equivalent to 0 mod 4. But then this is also 1 times 0, because 1 times 0 is 0, is equivalent to 2 times 0 mod 4. And because we have 1 times 0 is equivalent to 2 times 0, we cannot go backwards and say that 1 is equivalent to 2 mod 4. Like, we can't go this way. Because, of course, these two are not equivalent. One has a remainder of 1, and the other has a remainder of 2. So the purpose is we can't go backwards like this. And so this begs the question, when exactly can we go backwards? In other words, is there an integer x, or a type of integer x, such that ax is equivalent to bx mod n, implies that a is equivalent to b mod n? And the answer is yes, and this happens specifically when the greatest common divisor of x and n is equal to 1. Another way of saying this is that x and n are relatively prime. And relatively prime means that they share no prime factors. And how come this is true? Well, we note that ax is equivalent to bx modulo n only if and only if x times a minus b, which is the difference between the two sides, is divisible by n. And this one here happens if n divides a minus b. So we're only really missing this factor of x here. We want to get rid of this factor of x and make it such that n divides a minus b. But this x here does not share any prime factors or any factor greater than 1 with n, which means that this x is basically useless, so we just eliminate it. And therefore n divides a minus b. So a is equivalent to b mod n. All right, so now that we've analyzed these x which are relatively prime to n, let's go ahead and take a look at a key property of them. As it turns out, every single x with GCD of xn is equal to 1 satisfies a very peculiar property, that there exists an integer y such that xy is equivalent to 1 mod n. So in other words, when we multiply by y, we're basically undoing x, because now we just get 1, which when multiplied by anything is the same thing. So xy is equivalent to 1 mod n. And because two numbers multiply to 1, this reminds us of inverses when we're dealing with other things like real numbers or rational numbers. So we often abbreviate y is equal to x negative 1. All right, so now we're already better off than when we were with the normal integers. Because when we were working with the normal integers, only two numbers had a corresponding number that multiplied to 1 as well. 1 times 1 and negative 1 times negative 1. We can't have things like 2 times an integer x is equal to 1, because then x would be 1/2, which is not an integer. And modulo n, we're already a lot better off, because several numbers satisfy this property. However, not all of the numbers satisfy this property, only the ones which are relatively prime to n. if a number had a factor greater than 1 with n, then that means that this product here is always divisible by that factor. And so because 1 is not divisible by anything except for itself, that means that these two can never be equivalent mod n. So it's only these numbers x which satisfy GCD of x and n is equal to 1. X and n are relatively prime. And this begs the question, is there a way to make this true for all x? Is there a way to have GCD of x and n equal 1 for every possible x? Well, obviously this can't happen for every x, because, for example, we could have x equals n, and GCD of n and n is equal to 1, as is GCD of 0, no, is equal to n, as is GCD of 0 and n. So it makes sense to reduce to 1 less than or equal to x less than or equal to n minus 1. What happens if this GCD was equal to 1 for all of these x? Is there an n for which this is possible? And the answer is yes, and this is a very, very special type of number n, and you may know it as a prime number. And as you probably know, a prime number is a number which has only two factors, 1 and itself. And primes, you may know, are the building blocks of integers, and we're going to be exploring this idea further in the third and fourth videos of this series. But for now, what we need to know is that when n is a prime p, so let's go ahead and let n equals p for now, then we have GCD of x and p is equal to 1 for all x in this range 1 to p minus 1. And the GCD is only ever greater than 1 when x is divisible by p. And this makes working with integers modulo a prime p incredibly convenient. So let's go ahead and summarize all the amazing things that happen when working modulo a prime p. So we're going to be let me go ahead and clear this board real quick. So we're going to be first letting zp be the set of integers modulo a prime p. So this is going to be the set 0, 1, 2, all the way to p minus 1. And another way of notating this, if you want to, is by saying z pz. And if you know group theory, then you'll see why this is good notation, but I'll not discuss that in this video. Then we know that adding any or multiplying any two elements of zp gives an element of zp in return by simply taking the result modulo p. So for example, if I want to multiply like p minus 1 times p minus 2, then this becomes p squared minus 3p plus 2. And both of these guys are divisible by p, so we remove them. And this we have 2, and that goes there. And similarly, if we add them together, so if we add a plus there, then this is equal to 2p minus 3 normally, but we remove this 2p here, or we remove only one of them, and we get a p minus 3, which is somewhere over here. So yeah, adding or multiplying any two elements gives an element of the set in return. And obviously we have that adding 0 to any element, so n plus 0 just gives the same element again. And similarly, multiplying by 1, so n times 1 gives the same element in return. And then every element x has an element negative x, such that x plus negative x is equivalent to 0 mod p, or it's equal to 0 in this set here when we take modulo p. So x plus negative x is equivalent to 0. So far so good. We're doing everything the same as we were with the integers. But then here's a very, very interesting property. Every element that is not equal to 0, so not equivalent to 0 mod p, has a multiplicative inverse. So multiplicative inverse. And what this means is that there always exists an x to the negative 1 in the ZP, so inside ZP, such that x to the negative 1 is equivalent to 1 mod p. And this is a very, very, very powerful property. And because we have this multiplicative inverse property, we call this ZP here a field. And right away, I want to say that this is already really, really strong because the set of integers is not a field because, for example, 2 does not have a multiplicative inverse, as I said earlier. And a finite set being a field is already a big deal. The closest we can get to a field without relying on any primes is just a set of rational numbers, which is Q. So this should hopefully convince you of how powerful primes are and how powerful ZP is. It's incredibly structured, so we can do some really, really bizarre things. One such thing we can do is actually prove the following theorem. So suppose we have an integer a. Then, as it turns out, we have that a to the power of p is equivalent to a mod p. And this is known as Fermat's little theorem. And this holds for any number a. All right, so how exactly do we prove this? Well, the proof is gonna feel really random, but it's rather instructive in demonstrating the benefits of working modulo p, which is why I like this theorem so much. The proof is incredibly useful and gives a correct mindset when working modulo p, and it's also applicable to several areas in number theory. But first, let's go ahead and deal with a nasty culprit, which is a is equivalent to 0. And you'll see why it's a nasty culprit in a second, but for now, we just note that 0 to the p is equivalent to 0 mod p. So yeah, 0 is a culprit here. So let's suppose that a is not equivalent to 0. So a is not equivalent to 0. Then we can divide both sides by a in this equation, and this reduces to proving a to the p minus 1 is equivalent to 1 mod p. Okay, so now here's where the random part begins. So consider the numbers 1, 2, all the way to p minus 1. What happens if we multiply all of these numbers by a? Well, if we're working in the normal integers, then this is just a to a all the way to p minus 1a, and that's the end of the story. But when we're working modulo p, something interesting might happen. We'd expect something interesting to happen because we can definitely reduce a lot of these modulo p. So what happens if we work modulo p? Then could it possibly just be the same list of numbers again? So could this just be 1, 2, all the way to p minus 1 again? Obviously, this can't be the exact order, so it has to be in some order. In other words, is every number on this list here on this list over here, and vice versa? As it turns out, the answer is yes. And to see why, let's first prove that 1 is on the list. Then we need some number b times a is equivalent to 1 mod p. But this is just the modular inverse property. We can just take b to be a to the negative 1. So that proves that 1 is on the list. What about 2? Well, if we want to get 2, then we can just multiply both sides by 2. So then we get ba times 2, which is also equal to A times 2B, is equivalent to 2 mod P. And similarly, A times 3B is equivalent to 3 mod P. And so on and so forth. So therefore, every number on this list is also on that list, and clearly every number on this list, when we reduce mod P, is on this list. So therefore, these two lists are the same. And finally, to finish the proof, we multiply all the numbers on each side. The product of the numbers on this side is equal to, we have P minus 1 times P minus 2 all the way to 2 times 1. And then we have P minus 1 factors of A. So A to the P minus 1. And then we have P minus 1, P minus 2 all the way to 2 times 1 on this side here. And also I forgot to say that this is supposed to be equivalent, not equals, of course. So therefore, these two quantities are equal to each other. And then when we cross this out, because it is not 0 mod P, we can multiply by its modular inverse, because it has one since it's not 0, because there's no factor of P in here. We end up getting that this one here, this side is equivalent to 1 mod P. And this finishes our proof. But there's one thing we need to be careful of, and this is the reason why we checked A equals 0 to begin with. And the reason why we checked it is because we can't do this modular inverse step here. We cannot do this step here if A is equivalent to 0, because 0 does not have a modular inverse, mod P. So that means that we have to check 0 separately. And in fact, this more general version of Fermat's little theorem, or I guess more specific version, it does not hold when A equals 0. But this is the version we're going to be working with the most often, so it's important to know this form here, that A to the P minus 1 is equivalent to 1 mod P when A is not divisible by P. So now that we've explored a very fundamental property about mod P, let's go ahead and see our first example to see exactly what we can do. And our example is, if P is an odd prime, show that P divides the sum 1 to the power of 67 plus 2 to the power of 67 plus so on and so forth, all the way to P minus 1 to the power of 67. So how do we even get started on this problem? Well, the sum is already too big for us to compute on our own, since 2 to the power of 67 is already too large. For example, this value 2 to the power of 67, I think this is around 10 to the 18. It has 19 digits. So these numbers are way too large for us to work with. So therefore, it makes sense to work modulo P. But we are stuck. So because how do we reduce 2 to the power of 67 mod P? We may want to use Fermat's little theorem, but that doesn't help because 67 doesn't have a clear relation to the number P. So while we can't reduce that, let's go ahead and focus on what we can reduce. And we'll start with the first step. This one here is just 1. The first term is just 1, because 1 to the 67 is 1. But what about the last term? Well, this is P minus 1 to the 67, and because modulo P works nicely, we can just eliminate the P, and this becomes negative 1 to the 67 is equivalent to negative 1. But wait, because 1 minus 1 is equivalent to 0 mod P, these terms end up pairing up together, and therefore these cancel out. So we've just eliminated the first term and the last term from the sum. Can we try continuing this idea? Well, let's see. So we have 2 to the power of 67, and then P minus 2 to the power of 67. This is equivalent to negative 2 to the 67, which is also equivalent to -2, where the negative sign is outside, to the 67. And then these two terms pair up, and then we cancel out the last one here. And then we just continue pairing up terms in general. And in general, we pair up the term k to the 67 with p minus k to the 67 as well. And this ends up working out because we end up getting p minus k to the 67 is equivalent to negative k to the 67. And therefore, the entire sum becomes 0, and we are done. Or are we done? This is a huge issue, because we don't know if we are done yet. Because, you know why? Because we don't know if every number pairs up. For example, how do we know that the inner numbers in here actually pair up? And here's where a very weird thing comes in. If p is equal to 2, then the only number we have in our sum is 1. So that means that it pairs up with itself. And that means that if it pairs up with itself, we can't do anything with it. So therefore, we can't use p equals 2. And as such, we have that p being an odd prime is necessary. So yeah, p equals 2 is a really weird prime. And in the next video, we'll be evaluating the sum when 67 is replaced by any arbitrary integer k. Another important thing that happens when we're working modulo p is that perfect squares turn out really, really nicely. We'll be exploring this idea in the next video, but for now, let's go ahead and evaluate the perfect squares modulo 3. So we have 1 squared is equivalent to 1 mod 3, because it's just 1. 2 squared is equivalent to 4 is equivalent to 1 mod 3. And then 3 squared is equivalent to 9, which is equivalent to 0 mod 3. So our list of perfect squares modulo 3 is 1, 1, 0. Or if you start with 0, it becomes 0, 1, 1. Where did the number 2 go? As it turns out, the only residues which perfect squares can cover mod 3 are just 0 and 1. 2 is never a perfect square modulo 3. This is itself pretty powerful, as that means that no number equivalent to 2 mod 3 can be a perfect square. And we'll be seeing how this works in our example problem. And my exercise for you is to devise a similar condition when we work mod 4. You should get something really, really similar, but again, just work through the cases and see what you get. But for now, let's go ahead and take a step back from perfect squares and see how we combine everything together. You may be asking why we are even focusing on primes if they don't help resolve problems modulo n. Because if you look at a problem modulo a prime p, you may not know anything about the bigger picture when modulo n. Like if you work modulo 6 and turn it into a modulo 3 problem, you might not know what happens in the modulo 6 case. But actually, we do know what happens. And this is where probably the most important theorem in all of modular arithmetic comes in. And it is called the Chinese remainder theorem. So what exactly is the Chinese remainder theorem? Well, it starts off as this. Well, so suppose we have n1, n2, all the way to nk. These are all relatively prime. In other words, no two of them share a prime factor. The GCD of any two of them is equal to 1. Then for any integer x, the remainder when x, and we're going to be letting n be n1, n2, all the way to nk, be their product. Then that means that the remainder when x is divided by n has a unique one-to-one correspondence. There's a unique way to recover it from the set x mod n1, x mod n2, and so on and so forth, all the way to x mod nk. So that means that we can go from this way to here. We can have a bunch of residues modulo n1, n2, so on and so forth, and we can generate a unique residue class modulo n with this Chinese remainder theorem. And we can obviously go this way by just taking modulo n1, so on and so forth. But the Chinese remainder theorem states that this arrow here exists. In other words, that this arrow exists. And that means by prime factorizing a number n, we can almost always go back and forth between mod n and each of its prime power factors. So for example, if we want to look at mod 12, it is equivalent to looking at the problem mod 4 and mod 3, because 12 is equal to 4 times 3. So looking at mod 4 and mod 3 allows us to determine it mod 12. For example, if we know it's 2 mod 4 and 1 mod 3, then you can use it to solve it and get that n is equivalent to 9 mod 12. Wait, not 9 mod 12, but it's equivalent to 10 mod 12. Because 10 is equivalent to 2 mod 4, and 10 is equivalent to 1 mod 3. And the Chinese remainder theorem says that we can always do this. We'll explore this idea later in the course, where we can show equivalence modulo a complicated number by breaking it into smaller, manageable chunks. So how exactly do we solve number theory questions? I can't say much here right now since we haven't developed all the theory we need, but for now, here are a few pieces of very general advice for number theory. And the first one, which is probably the most important one, is to try special cases. Always try the special cases out. And special meaning small as well. So for example, if you know you want to find all the numbers n which satisfy a condition, so find all n, and you get that the n less than or equal to 20 which work are 1, 2, 4, 8, 16, you can probably guess very safely that the set of all numbers that work are just the powers of 2. So powers of 2. And by knowing the answer, you're able to figure out how you're supposed to prove it and what is so special about these powers of 2 with respect to the problem statement. And likewise, if you want to prove something for all n, then it's helpful to look at some small n and see what happens, because some small n could basically lay the entire groundwork for how the proof works. For example, n equals 15, this is a random example, can give an interesting pattern that you can explore further to make progress. All right, so that's trying special or small cases. And the reason I said special is because there's another type of case we can consider. And it goes under the second philosophy, that primes are your friend. Your friends. It's always helpful to look at things when we use primes, as we explored in this video, because primes behave incredibly nicely in number theory. And you can even use primes as your small cases in this above item here. And try not to overcomplicate problems. So what do I mean by not overcomplicate? Well, most of the problems we're going to be looking at in this course are on the problem 1 difficulty level. So if you use a Mohs scales in less than 15 or 20 Mohs. So as someone once told me, such problems almost always die to the simplest ideas. Don't get too ahead of yourself and always try out your dumb ideas. With that in mind, let's go ahead and look at an example problem. So here's our example. And this is an example from the 2017 IMO. For each integer greater than 1, define the sequence a0, a1, a2, and so on and so forth for n greater than 0 as follows. An plus 1 is equal to the square root of an if an is an integer, and an plus 3 otherwise. Determine all values of a0 such that there exists a number a such that an is equal to a for infinitely many values of n. So go ahead and try the problem out on your own first. Go ahead and pause the video and try it on your own. And when you're ready to discuss with me, hit the play button. Okay, so hopefully you've tried the problem by now, so let's discuss it together. So the first thing we must do in this scenario is understand what the problem statement means. So what exactly is an plus 1 here? Well, if square root of an is an integer, then we're just taking the square roots. And otherwise, we're adding 3. So basically, we're square rooting whenever we can, and otherwise we add 3. And we want to determine all values of a0 such that there exists a number a for which this is true infinitely often. So if this is true infinitely often, then we're just going to get stuck in a cycle. So the problem is asking whether we're going to get stuck in a cycle at any point. And let's see if we can prove for which values of a0 we get stuck in a cycle. Now let's go ahead and try out the small cases. Because a0 is greater than 1, let's try out a0 equals 2. Then 2 plus 3 is equal to 5. 5 plus 3 is equal to 8. 8 plus 3 is 11. No perfect square so far. 11 plus 3 is 14. 14 plus 3 is 17. 17 plus 3 is 20. So on and so forth. And it may seem really, really suspicious to you that none of the numbers in this sequence here that we've gotten so far are perfect squares. So we really want to prove that none of the an are perfect squares. In other words, that like 3k plus 1, the 3k plus 2 is not a square. And what do we do if we have a generic factor of 3 in front here? Well, if we want to prove that this is not a square at all, the one thing that all these numbers have in common is that they're all equivalent to 2 mod 3. And as I said earlier, numbers which are 2 mod 3 can never be perfect squares. So we're just going to keep going up and up and up because we're never going to get to a perfect square and decrease our number by taking the square root. So it's just going to continue like 2, 5, 8, 11, 14, so on and so forth forever. And we're never going to get stuck in a cycle. So that's why a0 equals 2 fails. And in general, because there's nothing really special about the number 2 except that it's 2 mod 3 in this case, that means that all 2 mod 3 fail. Okay, so what else can we do? Well, for one, we have a0 equals 3, which is next. Then 3 plus 3 equals 6. 6 plus 3 equals 9. 9 plus 3 is, oh wait, 9 is a perfect square. So we get back to 3. So our process begins to look like 3, 6, 9, 3, 6, 9, so on and so forth. And therefore we get stuck in a cycle. So a0 equals 3 works. What about a0 equals 4? Well, we want to increase by 3 to go from 4 to 7, but that doesn't seem to work because 4 square roots to 2 and we get stuck in a cycle again. Or we go not stuck in a cycle, but we go off to infinity and no longer get a cycle. So that's off the list. And similarly, a0 equals 5 is off the list. Now what about a0 equals 6? Then we go 6 to 9, then back to 3, then 6, then so on and so forth. So 6 also gets stuck in a cycle. The next interesting case is A0 equals 7. Because 7 is 1 mod 3, and 4 is also 1 mod 3, but we square rooted it immediately. So could 7 also work? Maybe. So if we go 7 to 10, not a perfect square, 13, not a perfect square, 16, and now we decrease it again. So we go back to 4, and that's also a perfect square, and we go back to 2. And then we just keep increasing and increasing and increasing, because it's again 2 mod 3. So that means that A0 equals 7 very weirdly fails. And then also A0 equals 8 also fails. And similarly, A0 equals 9. Wait, 9 is the square of 3. So we end up getting 9, 3, 6, 9, 3, 6, so on and so forth. And therefore, we get stuck in a cycle. So 9 works. And 10 doesn't work because we go 10, 13, 16, then we just repeat the process. So 10 doesn't work. So let me do that in a different color. So 10 does not work. So far the numbers that we have are working are 3, 6, and 9. And these numbers should look really, really familiar to you because they're just the multiples of 3. So therefore, by looking at our small cases, we conjecture that only the numbers which are multiples of 3 work. And this is our answer. But of course, we always have to prove our answer. That's what we must do. We can't just simply find the answer and be done with it. No, we have to prove it. And that's what we're going to be doing now. So we already know that 2 mod 3 fail. I'm writing it again here. And it really seems like the 1 mod 3 also fail. So we already proved that 1, 4, and 7 fail. Not 1 because it's not part of the problem statement. But 4 and 7 fail. And 10 fails because we go 10, 13, 16, and we go back to 4, which we already know fails. So I'm going to put an X here. Then what about the number 19? Well, 19 goes all the way up to 19, 22, 25. Then 25 goes all the way down to 5, which we know fails because it's 2 mod 3. So all of these numbers fail. The interesting case happens at 28. Then we go 28, 31, 34, 37, no perfect square yet, 40, 43, not yet, 46, 49, 50. Wait, no, 49 is a perfect square. It is 7 squared. So we end up going back to 7. But because we know that 7 fails already, that means that there's no way we can get 28 to be stuck in a loop. So 28 fails. So do all of these guys over here. And this suggests the following argument. Can we always reduce this number here to a smaller number for which we know it fails? Because after all, if we start with the number a and then go to some perfect square and go all the way back, then if we know that k is less than a and k failed, then that means that we know that a also failed. So basically what we're doing is if we prove that all the smaller numbers fail, that means that we prove that the number we're looking at also fails. And this is the idea of strong induction. Okay, so let's see how the details work out. So again, suppose I have a number, say 3a plus 1. And this is our 1 mod 3 number. Then if we have 3a plus 1, and the nearest perfect square to it is k squared, then we get to square root of k. And we want to prove that k is less than 3a plus 1. How exactly do we do this? Well, we can always assume for the sake of contradiction that the number k is greater than or equal to 3a plus 1. because if we can prove that this does not work in any world, then we are done. Then that means that this number here is greater than or equal to 3a plus 1 squared. Okay, so what's the next perfect square smaller than this number here? Well, that means that the next perfect square smaller than this one here is 3a minus 1 squared, at least the one that works, because it's 1 mod 3. But because this is the smallest perfect square greater than 3a plus 1, that means that this is less than or equal to 3a plus 1. And if we expand this out, we end up getting 9a squared minus 6a plus 1 less than or equal to 3a plus 1. Or equivalently, 9a squared is less than or equal to 12a. And that requires a to be less than or equal to 4/3. And the only way we can have this fail is if a is equal to 1, in which case we have this number here is 4. But we already know that 4 fails. So therefore, this is always true. We always go to a smaller number, and the smaller number fails. Or not always just a smaller number, which is 1 mod 3. The smaller number could also be 2 mod 3, in which case we already fail. But if we get to a 1 mod 3, then we just have the number in this list, which fails. All right, so now we know that all the 1 mod 3 fail. So let's go ahead and prove that all the 0 mod 3 work. So let me go ahead and erase all this. So yeah. So we know that 3, 6, and 9 all work. So let's see if 12 works. We would expect it to work because that's what our conjecture is. So we go 12, 15, 18, 21, 24, 27, then 30, add more to get 33. Not yet, but 36 is where we hit 6 squared. So we go all the way back to 6 here. But because 6 gets us stuck in our cycle, that means that this number here ends up working because we get to 36, which gets to 6 and gets stuck in our cycle. So all of these guys work. So again, we are motivated to use this idea of strong induction, where if we have a number 3k and we end up getting to a perfect square a squared, and then we go down all the way to a, we want to prove that a is less than 3k. Now, what happens if a is greater than or equal to 3k? Then that means that this a squared number here is greater than or equal to 9k squared. Now, what's the smallest perfect square divisible by 3, which is less than 9k squared? Well, it would just be 3k minus 3 squared, because we're just subtracting 3 from the component here. But because 9k squared is the smallest one greater than 3k, that means that this is less than or equal to 3k. And we'd expect a similar contradiction to hold. And indeed, we get something like 9k squared minus 12k, or this should be minus, I think, 21k plus 9 is less than or equal to 0. And whenever k equals 1, this is true, but 3 is part of our cycle. When k equals 2, we have this is 36 minus 42 plus 9, which is greater. So k equals 2 doesn't work, and when k equals 2, we're going to be going down, just like we do here. And then similarly, when we have 9, we go down here, and so on and so forth. So we're always going to go down and down and down until we get to a number which works. And therefore, we get stuck in this cycle here. All right. So therefore, we have solved the problem and proved that the only numbers which worked are the numbers which are divisible by 3. And don't get me wrong, this is a pretty hard problem, especially if you're starting out Olympiad number theory. The reason why I'm putting it as an example is because it demonstrates a few things I want you to know, especially about number theory philosophies. And the first one is to always try small cases. In this case, trying out the small cases up to 10 gave us a good idea for what the answer should be. Then the second idea is always try to quote unquote feel out the proof. In this case, we kind of felt out the proof before we did any details, where we realized that if we get to a perfect square, we're always going to get to a number that's smaller, and we're going to just keep getting smaller and smaller and smaller until we either get stuck in a loop or go off to infinity. So you try to feel out the problem first and feel out the proof before you work out any details. And of course, the third thing you should take away is that use mod n or mod p whenever possible. Because modulo p just makes it a lot easier to analyze this. All right, so what I have in the description is I have a handout. And the handout has a lot of the material I covered in this video, but it also has a bunch of exercises for you to try out on your own. I highly suggest working through the exercises. And if you need any help on the exercises, please leave a comment on this video with your progress on the problem, and I'll do my best to lead you on the right track. All right, I've said enough. Happy solving, and thank you so much for watching. See you guys in the next video.